the Mobius strip is actually two-dimensional, not three-dimensional. When you say two-dimensional or three-dimensional, what exactly are we counting?
Dimension does not simply mean the number of coordinates we use to locate a point on a shape. Here's the straight line y equals x plus 2 on a coordinate plane. Every point on the line has two coordinates, x and y, but there's only one direction you can move. And every point can be described using just one independent variable, t, t plus 2. So a straight line is one-dimensional. Now let's bend this line into a circle. The shape looks completely different, but has its dimension changed? A point on the circle can still be described using two coordinates, x and y. But you can still move in just one direction along the circle, and every point on the circle can be described using just one variable, theta. X equals r cosine theta, y equals r sine a theta. Once you choose theta, both x and y are determined. So we still need only one independent variable. That means a circle is also one-dimensional. Bending a line into a circle or into any other curve doesn't change its dimension. So dimension is not simply the number of coordinates used to locate a point. More fundamentally, it is the number of independent directions in which you can move on the shape. Mathematically, it's the minimum number of independent variables needed to describe a point on the shape. That number is the dimension of the shape. Now let's go back to the Mobius strip. At first, we have a flat strip. Since it is part of a plane, it is two-dimensional. Now twist the strip and connect its two ends. We get a Mobius strip. The resulting Mobius strip is bent in three-dimensional space. But just as bending a line into a circle doesn't change its dimension, bending and twisting a two-dimensional strip doesn't make it three-dimensional. The Mobius strip is still two-dimensional. Let's check this. Imagine you're at a point on the Mobius strip, and you move without leaving the surface. How many independent directions can you move? Two. One direction is along the strip, and the other is across its width. These two directions are enough to move in any direction on the surface. You don't need a third independent direction, so the Mobius strip is two-dimensional. Now let's confirm this by counting the number of independent variables. One way to construct a Mobius strip is to move a line segment while rotating it at the same time. The original line segment is one-dimensional, so a point on the segment can be described using one variable, v. Then we use another variable, u, to describe where the segment is along the circle. So every point on the Mobius strip can be written like this. If you'd like to know more about how this construction works, please check out the related video. Look at this equation. What matters is that all three coordinates are determined by just two independent variables, u and v. So there are three coordinates, but only two independent variables are needed, and that's why the Mobius strip is two-dimensional, even though it exists in three-dimensional space. If you enjoyed this video, help take this channel to the next dimension. A comment, one dimension, a like, two, a subscription. Now we're three-dimensional. Thank you.